and then share the screen, share content. Okay, so all of you can see the screen, right? The PowerPoint.
Yep, ma'am.
Okay, so let's wait for 2 more minutes for more students. How many students have joined so far? How many students have joined? There are some students, and then I will also note the attendance of everyone. Okay. So should I start, or I think we have to wait for 1 more minute, and we will start at exactly 3 o'clock. Okay. So today, yeah, we'll wait for 1 more minute and then we'll start because some students are not here yet. $2:59. Okay, now it's 3 o'clock. So I want to start with today's lecture now, which is going to be about wave properties of particles. Okay, so last time, was there any confusion about anything that we did last time? Last time was yesterday. It was just a basic introduction, okay, to all the different topics that we will cover this semester. And yes, it might have been a bit confusing because it was the first lecture, and I mean, it was just introducing you to all these different ideas, which we will cover in more detail along the semester. I hope it wasn't anything. Was there any? Is there any question related to any of the topics related to anything we covered in the introduction yesterday? Okay, well, if there's no question,
Ma'am, how
will
will
start.
we take the quizzes?
Sorry,
Quizzes.
quizzes MS Team पे ही होंगे, लेकिन उसके लिए I think मुझे delete करनी पड़ेंगी सारी जो uploads गई हुई हैं. Class materials for the quizzes. I will find out about that. I think MS Team पे ही होगा जिस तरह final exam हुआ था. लेकिन in that case, I would have to delete all the uploads. So I have to make sure about that. I will figure it out, okay? So today we will start with wave properties of particles. This is our chapter number 1. And in the book, which is this book, I hope you all have this book. I uploaded in the soft copies in the class materials. It's The Concepts of Modern Physics by Arthur Beiser, 6th edition. And it is chapter 3 of this book. Okay, it is chapter 3 of this book. And in this book, we have chapter 1 is about relativity, which we will do later on. We have chapter 2 is particle properties of waves, which we'll also do later on. According to the course outline, we have to start with wave properties of particles. So that's going to be our first chapter. And then chapter 4 in the book is atomic structure. We'll be doing that as well, quantum mechanics, etc. So I want to talk to you about wave properties of particles. So these are revolutionary ideas which came around the late Einstein के time में के करीब ये ideas आई थी. Wave properties, that particles can have wave-like properties and waves can have particle-like properties as well. These are revolutionary ideas, and this is referred to as wave-particle duality, basically. Why do we say duality? Because both things can exist. However, at one time, if you have a particle, it can have wave-like properties, but at one time, if you're observing it, it will either reflect the particle-like properties or wave-like properties. Both will not be existing together at the same time. Like at one particular time, if you're observing a particle and it can, if you're able to measure its momentum and its velocity, it will have particle-like properties, okay? But if it exhibits diffraction or interference, as I will show you in the coming slides that we have, that's actually in the next PowerPoint. I will show you about electron diffraction and those experiments which were used to prove this wave particle duality principle. Okay? So basically what this Louis de Broglie in 1924, he proposed that moving objects have wave-like properties as well as particle characteristics. Okay? So the existence of the de Broglie waves, 1927 में we don't need to really know the history, but 1927 में existence of de Broglie waves was experimentally demonstrated, ठीक है? And then Schrödinger he developed, and then later on, once the wave-particle duality was confirmed by experimentation using electron diffraction, by electron diffraction and other experiments, photoelectric effect, etc. Then we will do all these experiments. We will go through all of these. Don't worry about that. Okay, we will do all of these. And then afterwards, Schrödinger came, and then he developed quantum mechanics. Okay. So now let's talk about de Broglie waves. What do we mean by a de Broglie wave? Any idea? So basically, if we have a particle, okay, a particle, we said before that a particle can have a wave-like property as well. Okay, it can have wave properties as well. So we know that a particle can have momentum, which is given by P, the momentum of a particle. We know. So so what is this principle is basically says that a moving body behaves in certain ways as though it has a wave nature. So a particle that's a moving body, a body that's stationary will not have a de Broglie wave, okay? It won't have wave-like properties, but a moving body can have wave-like properties. So we all know that a photon, what is a photon, basically? A photon is a packet of energy, right? Light consists of photons. So we know that photon can have frequency. We know that the energy of a photon is given by HF, yes? We've studied this in astronomy and astrophysics. So the energy of a photon is given by E is equals to HF. Oh, wait, is this recording? Yes, it is. Okay, sorry about that. And so the de Broglie wave is given the momentum. So this basically this equation de Broglie, this wavelength over here is known as de Broglie wavelength. It is given by H over P. Basically, momentum of a photon of light that has frequency nu has the momentum P is equals to E over C. So if I are you all following this? So basically the formula for de Broglie wavelength, which is this formula, okay? De Broglie wavelength is given by lambda is equals to H, which is the Planck's constant, divided by P, which is the momentum of the photon. So this is basically the formula for de Broglie wavelength. This is de Broglie wavelength. Like, what do we mean by de Broglie wavelength? What we mean is that if there's a body which is like a particle, it's moving, it can have wave-like properties. And when it has wave-like properties, it obviously has some wavelength associated with it. Doesn't that make sense, right? Because if it has wave-like properties, if it can exhibit diffraction, interference, wave-like properties, the basic properties of a wave is that it has some amplitude and some wavelength, yes? So basically, when a moving body can behave as though it has a wave nature, and in that wave nature, it will have a wavelength known as de Broglie wavelength. That is a wavelength associated with a moving body that has a wave-like nature, And that formula is given by H over P, where P is the momentum of the particle. Okay? This formula is just the inverse of this one. Okay? If you just put P over here, then you will get H P is equals to H over lambda. This is the definition of the momentum of light. This is the momentum of a photon of light that has frequency nu. We know that HF, this term over here, is equal to the energy of the photon, yes? HF is the energy of a photon. We know that. And I'm saying F because we're used to F as frequency rather than nu, but in this book, they've used nu, this symbol nu for frequency. So I hope you don't confuse it with velocity, because velocity is V and frequency is nu, but they're two different things. They're two entirely different things. So this equation makes sense. Like this is how it's defined. To get the de Broglie wavelength is defined in this way. I hope this makes sense. And then, as I said before, that a little bit of special relativity will be used in this chapter. That's why I had said previously that if we wanted to start with relativity, or do we want to start with this chapter? So I hope, and because we're starting with this chapter, we have a little bit of relativity. Like I will say that we talked about gamma last time in last lecture. Gamma is equals to what? Do you all remember what gamma is equals to? Let me open that PowerPoint as well. Oh wait, actually I have it in the next slide. This one, gamma is a relativistic factor which is equals to 1 over square root 1 minus v square over c square. Well, what is v in this case? V is the velocity of the frame of reference. Okay, we have two frames of reference. Is this all making sense to all of you?
मैंने अभी तो स्टार्ट किया है पूरी बात
Yes,
कंप्लीट
ma'am.
करें फिर
Making
पता चलेगा
sense.
Okay. So if we have, if I want to write on the board, it's difficult because I have to always like stop the screen share, and then I don't know. Well, I was telling you about two frames of reference. Let me open that other PowerPoint as well. Maybe we might need some of that information from there as well. Okay. So I hope you all can see this. Can you see this new PowerPoint? Yesterday's PowerPoint? Yes. Okay, so ये यहाँ पे हम देख रहे हैं कि दो फ्रेम्स हैं, ठीक है, रेफरेंस फ्रेम्स. हम उनको कोऑर्डिनेट सिस्टम्स की तरह एक्सप्लेन करते हैं, दिखाते हैं, because every like coordinate systems are used to they're used to pinpoint the position of a particle, right, of an object, moving object. Like coordinates के साथ हम उससे कहते हैं कि ये ऐसे move कहाँ, where it is at a specific point, where it's positioned at a specific time. So if you have a moving frame and one frame is moving with velocity v relative to the other frame, then gamma is a relativistic factor which is given by 1 over square root 1 minus v square over c square. And we'll be using this in this chapter as well as the chapter on special relativity. So to go back to the previous PowerPoint, this is called gamma, and it's the relativistic factor, okay? So so what I want to say, go back to the previous slide. So relativity may we have two things. Classical momentum, when we know that momentum is what? mv, right? This is classical momentum, mass into velocity. But relativistic momentum is gamma mv. Momentum is equals to gamma mv. Relativistic momentum is when the velocity is close to the speed of light. Okay? So for example, I think I will have to use a board. So should I exit this share or what? How do I do this? Hide share options. Yeah?
मैम ऐसा
Yeah?
कर ले, अपने साथ माउस रख ले और इसी लैपटॉप में पेंट ओपन करें, उस पे राइटिंग करें.
I know. यहाँ पे भी व्हाइट बोर्ड है.
यस मैम, वो मुश्किल हो जाता है फिर बार बार स्क्रीन शेयर को ऑफ करना.
इस पे वो मुश्किल हो जाएगा. तो यहाँ पे भी व्हाइट बोर्ड है. Wait, let me see. यहाँ नहीं आया व्हाइट बोर्ड.
ब्लैक बोर्ड आया है मैम.
Yeah, okay. Present whiteboard, only you can edit. Present whiteboard. Okay, now we have a whiteboard on the screen. All of you can see it?
Yes,
sir.
Okay, so gamma is equals to, we all know what gamma is equals to. So let me erase this for now. And then let me write that we know that momentum, classical momentum is equals to mv. ये हम सबको पता है, yeah? But in relativity, when speed is close to the speed of light, we have momentum is equals to gamma mv. Okay? And in this case, v can be, say, some fraction of c, like 0.5 c, 0.8 c. I'm just giving an example for now. For example, it's 0.8 c or something like that. Okay? So now if I go back to the PowerPoint, and one more thing I want to mention before I go back to the PowerPoint, and in classical mechanics, energy, rest energy is given by E is equals, you must have done this before, right? MC square. Have you done this before? And then relativistic energy when speed is close to speed of light, like for example in this situation. So E is equals to gamma, E is equals to gamma mc square. This will be the total energy. Is this all making sense? Where we know what gamma is, we know where gamma is. Gamma is equals to this relativistic factor, 1 over square root 1 minus v square over c squared. ठीक है? तो ये मैं अब मैं PowerPoint की तरफ दोबारा आ जाती हूँ. I will share the PowerPoint again. Okay. So what I'm saying here is that we will talk about relativistic effects as well as non-relativistic effects. So in the case that momentum of a particle, if we're talking about relative velocities close to speed of light, then momentum will be equal to gamma mv. और अगर हम lambda is equal to hp over p.
मैम जाजिब कुछ कह रहे हैं.
Yeah. A question?
यस मैम, वो मुझे पूछना था कि ये ऐसा क्यों होता है.
क्यों होता है वो हम स्पेशल रिलेटिविटी में डिराइव करेंगे ना. उस चैप्टर में गामा को डिराइव करेंगे. मैं सारे इक्वेशंस उसी चैप्टर में डिराइव करूंगी बिकॉज आई सेड बिफोर दैट हमें थोड़ा सा रिलेटिविटी चाहिए होगा इस चैप्टर में. इसलिए मैंने पूछा था कि हमें शायद रिलेटिविटी करना है या ये चैप्टर पहले करना है. तो आई डोंट नो व्हाट यू वांट बिकॉज इसमें थोड़ा सा रिलेटिविटी आता है. और वो जब गामा को मैं एक्सप्लेन करूंगी कि गामा का फैक्टर कहाँ से आता है और ये मोमेंटम गामा mv क्यों होता है और एनर्जी गामा mv mc स्क्वायर क्यों होता है, ये सारा रिलेटिविटी के चैप्टर में आएगा. लेकिन इसमें थोड़ी सी उसकी एप्लीकेशन है. या
मैम हमें तो इस कोर्स का नहीं पता, आपको लेकिन पता है, तो जो आपको बेहतर लगता है आप वहाँ से स्टार्ट करवाएं.
But I think this chapter, I had a suggestion from some students that we should start with this chapter, so that's why I started
स्टूडेंट्स
with
को
this
क्या
chapter.
पता, स्टूडेंट्स सेकंड लास्ट चैप्टर से कहते हैं तो आप वहाँ से पढ़ाने लग जाएंगे.
या मैं जो आप बेहतर लगता है वही करें.
Okay, then if you don't understand this, अगर ये आप लोगों को अभी समझ में नहीं आ रहा कि गामा क्यों हो रहा है, फिर I think we should start with special relativity then.
यस मैम.
एक्सक्यूज मी मैम.
Yes.
मैम मैं मुताहिर की बात से एग्री करूंगा. आप सिचुएशन को मद्देनजर रखते हुए ना, मतलब आप ऑनलाइन वो कोर्सेज डिलीवर करें जिसके अंदर कम से कम डेरिवेशन हो और बनिस्बत दूसरे चैप्टर्स के इजी हो ज़्यादा.
Yeah. But this, I want to tell you all that this course is not going to be as easy as astronomy courses. इसमें काफी mathematics हैं. So I want you to like listen carefully and everything. So do all of you agree that we should switch to relativity first?
मैम
नहीं, वो आपकी बात ठीक है,
नहीं, मैम.
लेकिन सीक्वेंस बनता ही नहीं है. जहाँ पर वो थोड़ी सी अटेंशन आती है, कोई ना कोई वो एस्केप कर देता है रूम से, तो दरमियान के अंदर ही वो मोशन सारा टूट जाता है. तो
मैम
आप
अगर आप
मतलब
फॉलो
आप
कर रही
दूसरे बच्चों को पढ़ाया चुप कर पे.
अगर आप बुक फॉलो कर रही हैं मैम तो उसी के चैप्टर फर्स्ट से स्टार्ट करें.
Yes, that's what I was saying. I was saying that according to course outline, this was the first chapter, but I think we should start with relativity. Okay, let me go
मैम
to
अगर ये
relativity.
फर्स्ट चैप्टर है तो फिर तो कुछ मसला नहीं है.
नहीं, book में first chapter relativity है, लेकिन according to the course outline, they put the chapter of waves, this chapter first.
मैम
इसलिए
सजेशन यही होगा कि बुक को फॉलो करें मैम.
Yeah, okay, let's start with this chapter then, special relativity. Okay. Can all of you see the screen? Let me just share the screen again. Can all of you see the screen?
Not yet
The
मैम.
PowerPoint. ये वाला PowerPoint, ये वाला.
No, ma'am.
नहीं आ रहा? Okay, let me hide the screen and then share again. Okay, here. So we will start with special relativity because that is the first chapter of the book, and in order to understand wave properties of particles, you need to have a basis of special relativity. So I hope you're all familiar with classical mechanics. Okay, classical mechanics we have Newton's 3 laws of motion, and you're all familiar with those. I don't need to repeat that because I already said that in the last lecture.
Yes,
So special relativity में हम सब gamma और ये सब कुछ derive करेंगे. What I just told you on the whiteboard was that momentum relative. We know that classical momentum is given by P is equals to mv, and classical energy, rest mass energy, is given by mc square. But when we go to relativity, we have P is equals to gamma mv, and P is equals to gamma mv, and energy is equals to gamma mc squared. So we need to be able to derive these equations. So we will derive these now. So basically, Albert Einstein, we're starting with special relativity. He showed that measurements of time and space, they are affected by motion between an observer. Like, can I first give you a situation? Like, if you're on the Earth, right, you will think that the sun is moving around the Earth, right? But if you're on the sun, you will think that the Earth is moving around it. So basically, what special relativity says is that there is no universal point where we can say, there's no universal frame where we can say that something is moving. Like, for example, let me use a whiteboard again. But all motion, basically what we're trying to say is that all motion is relative. There's no absolute motion. Does that make sense? Like, we are saying that the sun is moving at, say, the Earth is moving at a speed of this much, we can say, but we have to say that it's relative to something, relative to what, the sun, for example. So basically, we're saying that all motion is relative. There's no such thing as absolute motion. Does that make sense? I hope that makes sense. So Einstein, he came up with this theory of special relativity. He also did general relativity, but general relativity is a totally different concept, okay? So we're not going to be doing general relativity, but we will be doing special relativity. And relativity, it connects space and time. We'll be doing Lorentz transformation as well. And mass and energy and momentum, these topics, things we'll be covering. So what we want to understand is that what do we mean by motion? Basically, we mean that a motion of an object is that it's moving relative to something else. So a passenger, for example, is in an airplane. So the airplane is moving relative to the Earth. But what do we mean? Does it have any weightage to say that the airplane is moving absolutely, like universally? No, because it's always moving relative to something. So we need to have frames of reference, basically, to describe motion. We always say that something is moving relative to something else. So basically, we have something known as inertial frame of reference. It's something in which Newton's first law, it's a frame of reference in which Newton's first law of motion holds, okay? So we know that first law of motion says that if an object is at rest, is without any forces acting on, there's no force acting on it. So it's going to remain at rest as long as there's no force acting on it. And if the object is moving, then as long as it's moving with constant velocity and no force, then no force acts on it. There's no acceleration. We know this stuff very easily. This we've studied, you've all studied this in metric, FSC, etc. or OA levels. So basically, any frame of reference that moves with a constant velocity is an inertial reference frame, relative to an inertial frame. So we will be talking about inertial frame of reference. And an inertial frame of reference is one in which Newton's first law of motion holds. If a frame of reference, if a frame like a coordinate system that I was talking to you about, a coordinate system is like one frame, XY with XYZ axis. If it's moving, if it's accelerating, that is not an inertial frame of reference because it has acceleration. There are some forces acting on it. It's not moving. It's the frame is not, the frame will be either at rest or moving at a constant velocity. Okay? If there's some forces on the frame, reference frame, it's accelerating, that is not an inertial frame of reference. So we're saying that all inertial frames of reference in which Newton's first law of motion holds, they're all equally valid. Like, we don't prefer one frame over another. We don't say that one frame is better than another frame or this is more universal than another frame. They're all equal in our perspective. Okay? So suppose we are seeing something changing its position, okay, at a constant velocity. So the question now is, if I am sitting here and if I see an airplane moving in the sky, will I say that the airplane is moving, or will I say that I am moving relative to the airplane? Or am I moving? Because either way it can work, right? Like if there's the sun and the earth, or say the earth and the moon. So as for an observer on the earth, the moon is moving, but if you're on the moon, you will think that I'm at rest and that the earth is moving around it. So everything, all of this motion is basically relative. There's no universal frame of reference that we can use everywhere. There's no such thing as absolute motion. Any questions so far? No? Okay.
मैम जब हम
Yes.
एक जुमला बोलते हैं कि फ्रेम पे फोर्स लग रही है तो इसका क्या मतलब है मैम?
फ्रेम के अंदर कोई ऑब्जेक्ट हो, like frame for example an airplane, ठीक है? There are passengers sitting in the airplane. So airplane can be like a frame. For example, if it's moving at constant velocity, then it's an inertial frame of reference. उसके अंदर कोई objects हैं जो भी move कर सकते हैं. Like you can walk inside an airplane, right? तो हम उस passenger की बात करेंगे कि like the airplane is a reference frame. The passengers, if the airplane is moving at constant velocity, फिर तो frame जो airplane का frame है वो it's an inertial frame. But if it's accelerating, then it's not an inertial frame. In that sense, we can consider a frame to be something in which there is another object that may be moving or not moving or at rest or something like that. So then you will consider the Earth here, observer on Earth, and a passenger that's in an airplane. The passenger can walk inside the airplane, but so the airplane will be the frame. Does that make sense?
Yes, ma'am.
Okay, so a frame is like basically a frame. Yeah.
क्या हम ये कह सकते हैं कि जो अभी हमारा अगर यूनिवर्स को हम ऐसा एज अ फ्रेम लें तो यूनिवर्स क्योंकि एक्सपेंड हो रही है तो ये नॉन इनर्शियल फ्रेम
universe में forces होते हैं, like I mean you have to think about, you have to divide it into smaller things, right? You can't just say universe as a whole because वो accelerate तो कर रहा है ना universe. तो पूरा universe तो inertial frame कैसे हो सकता है अगर वो accelerate कर रहा है उसके forces हैं तो
जैसे मैं वही पूछ रहा हूँ कि एक्सेलरेट कर रहा है इसी वजह से हम कह सकते हैं कि वो नॉन इनर्शियल फ्रेम ऑफ रेफरेंस
या नॉन इनर्शियल फ्रेम because it's accelerating. So you have to divide, like you have a system, you will divide it into different components, and then you will say that if this part is moving, it's at rest, then basically that will be an inertial frame. Like if an aircraft is moving with a constant velocity, then that is the inertial frame of reference जिसके अंदर दूसरे objects हैं जो कि move कर सकते हैं. Here we will want to determine how, like if the aircraft, like for example, if we have a whiteboard, I think I need to use a whiteboard, and like I mean what I'm trying to say here is that if you have did you understand the aircraft example, aircraft and earth example? How do I can I erase it? What is this? This is a bit confusing. What is this? Okay, so basically, ये क्या बार-बार हो रहा है? Sorry about this. I don't know what this is.
कोई मसला नहीं है, take your time.
Okay. I think to understand these concepts, we need a lot of time to basically understand all these ideas. So don't worry, we have time in the semester. We will understand everything properly. We won't skip anything because these concepts are very important. Okay, so basically what I'm saying is that if I'm an observer over here, okay, observer here, and this is an airplane, so then there's another observer over here, another person inside the aircraft. So the person can walk in this frame, but the frame itself is moving with a certain velocity, yes? But it's a constant velocity for it to be an inertial frame. So if this is moving with the velocity v1 and this is moving with the velocity v2, and we are an observer who's at a frame of reference that is at rest, then how will we observe the velocity if this velocity is close to the speed of light? Again, this velocity is close to the speed of light, then how will we quantify what will be the velocity of this object in this reference frame as seen by an observer at rest? These are some questions we want to be able to answer in this course in special relativity. Does that make sense? Like, will we simply add v1 plus v2? It seems as if we have a coordinate system like this, and agar ye rest mein hai, ye observer rest pe hai, in a frame that's at rest, on Earth, for example, in one particular country on the Earth. Okay? And over here we have an aircraft moving in the x direction with velocity v2, which is, suppose it's close to the speed of light. Obviously the aircraft won't move that fast, but if it's a spacecraft or like a rocket, then we have an astronaut in the rocket and it's moving with velocity v1. Will we simply add these two velocities? What do you think? So that's the whole point of special relativity, that's Galilean transformation, where we just simply add the two velocities in. If it was not a relativistic situation, like the velocity is not close to the speed of light, then in a normal situation, we would simply add these two velocities, right? The velocity of this, because this passenger is moving at velocity v1 relative to this aircraft, and this aircraft is moving with velocity v2 relative to the Earth, right? So we would simply add these two in a non-relativistic situation to give a final velocity of v1 plus v2 of this object relative to this.
मैम जो हम फाइनल वेलोसिटी निकालेंगे ऐड करके नॉन रिलेटिविस्टिक इफेक्ट में, वो किसकी होगी?
वो इस object, this passenger, relative to this frame, relative to this passenger that's at rest on the Earth.
पैसेंजर की होगी जो उसके अंदर? यस मैम, ठीक.
Yeah, so because this one is moving at v1 with respect to this frame, and this frame is moving at v2 with respect to this frame, तो फिर total sum हो जाएगा ना, add करेंगे ना, तो वो Galilean transformation कहते हैं इसको. It's simple addition of the velocities, but special relativity में ऐसा नहीं कर सकते, ठीक है? Special relativistic effects में, special theory of relativity में, if the velocity of the frame is close to the speed of light, then we cannot simply add them to these two together. We have effects called, we have the Lorentz transformation, and we have time dilation and length contraction, and we have the gamma factor. So now I will go back to the PowerPoint. And where are we now? The theory of special relativity basically applies when we consider that there is no universal frame of reference. All frames are relative to one another, okay? So now let's talk about the postulates of special relativity. The first postulate says that special relativity, the principle of relativity states that the laws of physics are the same in all inertial frames of reference. So basically, if we have an inertial frame of reference, as I said before, a frame, for example, that's not moving, that's stationary, okay? Then, or moving at a constant velocity, as I discussed before, those are inertial frames of reference, basically ones in which Newton's first law applies. So the postulate follows from the absence of a universal frame of reference, okay? All the laws of physics will apply in the inertial frame of reference. The second postulate is based on the results of many experiments. It's that the speed of light in free space has the same value in all inertial frames of reference, which is 2.998, or approximately 3 × 10⁸ meters per second to 4 significant figures. So speed of light has the same value in all inertial frames of reference, okay? So in an inertial frame of reference, in which Newton's first law applies, in which if the frame is moving, if either is at rest or moving with a constant velocity, it's non-accelerating reference frame. The speed of light will be like this, and now we will talk about time dilation. And in this time dilation, is everything making sense so far? We're going to derive this gamma factor. We're going to derive the gamma factor. I'm going to go through all these slides and we will derive this gamma factor. We will prove that T is equals to T naught over 1 time. T is equals to gamma T naught. So any questions so far? I will tell you what time dilation is in a moment. So let me just time dilation and length contraction. Let me just talk about time dilation now, if there are no questions. Basically, what happens is that if you have special relativity, we cannot just add those two velocities as I mentioned before, okay? There will be other effects which will take place. Some of those effects, two of those prominent effects that take place are known. One is known as time dilation. What do you mean by dilation? Is that increase in length or size. So time dilation means the time is extending. So if I have, you must have watched the movie Interstellar or something that's related to astronomy. So basically, if I use the whiteboard again, okay, so it takes some time to load. Now I will erase this stuff. Okay, so now what I'm saying here is that if you have a frame here, and frames are usually represented by coordinate systems. ठीक है, ये थोड़ा सा curvy बन गया. We have frames are represented by coordinate systems because if an object is over here, ठीक है, उसके coordinates होंगे x, y, and z, ठीक है. So now we have another frame over here, ठीक है. Now this frame is moving with a velocity v in this direction. Now, for example, if this velocity is relativistic, what can I say about, say for example, you have a clock, you have a mirror over here, and you're sending a light pulse out there. It reflects from here, it comes back over here. ठीक है? ठीक है? So we need to use the board a lot in this course actually to be able to understand the concepts, but I hope this whiteboard is okay for now, and I'll see if I can do something about that whiteboard. So if you have a frame that's moving at velocity v of like this in this direction, and you have this one is at rest, okay, an object here, observer here is at rest. v1, this one's velocity is 0. This frame is not moving. This frame is moving with v relative to this frame. ठीक है? So this one is at rest. So now if I have now what's going to happen to this situation? Like if this is a ticker, like a clock, okay, we want to measure the time it takes for, if I'm sending a light pulse out at this moment over here, and time is t is equal to 0, and then I'm sending the light pulse out over here, it's going to reflect over here, and then it will come back. So now let's go back to the PowerPoint. Moving clock. What I want to do, what my goal is here, is that I'm going to say that if I measure a time interval t as measured from this t0, if there's a time interval between two events, t0 in this frame, then t as measured, the time interval delta t that I measure in this frame as seen from this frame, it will be larger as seen from this frame of the event that took place in this frame. Is that making sense? For example, like if there's a clock over here in this frame, it's like a spacecraft, a rocket that has gone to the moon, for example, or outer space. अगर उस rocket के clock में 1 साल गुजर गया by the time it reaches back on Earth, as seen from the Earth that is at rest with respect to the spacecraft, the spacecraft would have moved, say, gamma times that 1 year. So gamma factor is always greater than 1. Why is gamma factor always greater than 1? Let's see right now. 1 over square root 1 minus v squared over c squared. ठीक है? So this factor over here, V will always be less than C. It can, for example, if it's 0.5, 0.8 times C. So this, what will happen to this factor? What will happen? 0.8 times C will cancel. C square will cancel with C square. We will get 1 minus 0.64, 64, right? 0.64. 0.8 square is 0.64. And then 1 minus 0.64 is 0.36. So square will be 0.6. So basically what I'm saying is that if you're dividing by square root of 1 minus a fraction, this is going to be a fraction, a decimal number, because V is always less than C. It will be a fraction of C. So if this is a fraction, squared will also be a fraction, a decimal number less than 1. 1 minus something less than 1 square root will be, what will that be? Something also a fraction. So 1 divided by fraction will be always greater than 1. Is this making sense?
Yes, ma'am. मैम लेकिन ये बता दें टाइम डायलेशन की समझ नहीं आई सही तरह से.
The time dilation में अब पूरा एग्जाम्पल हम करेंगे, अभी फिक्र ना करें, ठीक है? इसका पूरा एग्जाम्पल करेंगे अभी मैं ये बताना चाह रही हूँ कि T will be as measured from this frame, T will be equal to gamma T 0. ठीक है? यहाँ पे हम actually इस डेल्टा को हटा देते हैं. ठीक है? So what I'm saying here is that if you measure like a spacecraft that's going close to the speed of light, if it's going to the moon and it comes back, 1 साल गुजर गया है spacecraft की clock में. लेकिन to an observer on Earth, that 1 year will not be one as measured from the observer on this in this reference frame that's at rest with respect to this frame, that will measure a longer time, which is gamma given by gamma of this time. And gamma is 1 over square root 1 minus v square over c square, where this is v, here is the velocity of the reference frame. And now we're going to derive this equation. How we got it, okay? So now I will exit the whiteboard. Any questions so far? I will exit the whiteboard and turn on the screen, yeah? Sorry? अभी इतना हमने बहुत थोड़ा सा किया है अभी आज. Okay, let's see if we can try to do one derivation right now. Okay, so what I'm saying, yeah.
मैम आज ना करें डेरिवेशन,
10 मिनट
कल से करते हैं.
10 मिनट में इतना कर सकते हैं, ये कर सकते हैं, यहाँ तक तो कर सकते हैं.
मैम टाइम डायलेशन का कांसेप्ट को समझा रहे हैं जैसे कि वो जो ऑब्जर्वर होता है अर्थ पे, उसके लिए टाइम ज़्यादा क्यों होता है एज कम्पेयर टू जो ऑब्जेक्ट होता है वो जो स्पीड ऑफ लाइट से मूव कर रहा होता है. ये थोड़ा इमेजिन करना मुश्किल है, लेकिन
whiteboard. Okay, so what you were saying, you were saying that explain the concept of time dilation again. Okay, so what I'm saying is that for example, you have 2 reference frames. ठीक है, एक ये frame है जो कि rest में है. ये frame rest with respect to this frame. ये frame है, for example, a spacecraft that's moving in with a velocity v. Like for example, आप ऊपर जा रहे हैं. Can I use this whiteboard, this one? अगर मैं इसको बंद करके hide share option. अब can everyone see my video?
No, ma'am.
वीडियो नहीं नजर आ रही?
मैम स्क्रीन बहुत छोटी सी नजर आ रही है, वो स्क्रीन शेयर ही हुआ, वो व्हाइट बोर्ड नजर आ रहा है.
ओके, इसमें किस तरह हम अनडू करेंगे इसको? How do I close this? बहुत टेक्निकल इश्यूज आ रहे हैं इसके यहाँ. Okay, now I think, ठीक है? So how I want to pin my video. I want to make it larger. Can all of you see? इसको किस तरह large करें? Yeah.
मैम अगर पॉसिबल हो नेक्स्ट क्लास से आप ऐसा करें ना कि एक प्रॉपर पोजीशन में लैपटॉप रख लें और पीछे जो ये बोर्ड है ना कि ये सारा नजर आए।
अब नजर आ रहा है बोर्ड, लेकिन वीडियो बहुत छोटी आ रही है।
बहुत छोटी है ना वो उसमें।
सर नेक्स्ट मैम
लेकिन मैम हम लोग उसे पिन कर सकते हैं ना, हम अपने लिए तो पिन कर सकते हैं आपकी वीडियो।
या लेकिन मेरी रिकॉर्डिंग में नहीं नजर आएगा ना, मेरी रिकॉर्डिंग में बहुत छोटा नजर आएगा।
यस मैम, ये तो है।
रिकॉर्डिंग में भी बहुत नजर आएगा। आई विल यूज दिस व्हाइट बोर्ड देन अगेन। यस
मैम ये आप क्लास में तो नहीं पढ़ा रही ना, मतलब ऑफिस में बैठी है?
मैं अभी किसी क्लासरूम में बैठी हुई हूँ।
तो फिर मैम ऐसा करे जिस तरह आप क्लास में वो पढ़ाती थी ना, जब बोर्ड वर्क आता था तो आप बोर्ड यूज करती थी और जब स्लाइड्स आती थी तो वो पावर पॉइंट का प्रोजेक्टर आप यूज करती थी।
से करना होता है ना, और फिर वो मेरा जो व्हाइट बोर्ड था घर वाला, वो घर में पड़ा हुआ है। I'll have to see what to do. I will figure something out, okay? So basically what I'm saying
नहीं है वो, अगर आप रिकॉर्डिंग तो हम भी यहाँ से कर सकते हैं, तो अगर आप वो कर लें उस बोर्ड को यूज़, तो रिकॉर्डिंग सीआर वगैरह करके वो भेज दिया करेंगे।
Okay, I will see. हम discuss कर लेंगे, ठीक है? So what I'm saying is that if you have the Earth is over here, ठीक है? The Earth you have over here. The Earth is this thing. This is the Earth, and this is a spacecraft moving this upwards, and then it comes back down. So if it's moving close to the speed of light, then by the time it returns, उसके लिए अगर एक साल गुजरा है तो इस observer के लिए, which is at rest relative to this observer, उसके लिए time dilate हो जाएगा। वो इवेंट जो कि उसके जाने और वापस आने तक आएगा, the gamma we will multiply a factor of gamma to that time interval. I hope that's making sense. And we're going to derive this equation. I want to derive this equation. Like, I hope I can try doing that now. There are still 5 minutes left. We can still try.
हम 6 वक्त में तो नहीं होगा।
So consider a light pulse, okay? A clock is at rest over here. So अभी तक समझ में आ गया टाइम डायलेशन होता क्या है और स्पेशल रिलेटिविटी होती क्या है? गैमा फैक्टर होता है एक, जिसकी वजह से टाइम डायलेट हो जाता है और लेंथ ऑन द अदर हैंड कॉन्ट्रैक्ट हो जाता है। These are two important concepts I want you to all know very clearly, ठीक है? Is it making sense to everyone?
थोड़ी मैम।
थोड़ी okay, ये हम एग्जांपल भी करेंगे और डिराइव करेंगे। Can we do this now, or I think we should do this now. Okay, so to see how time dilation comes about, let's consider two figure 1.3 for example. एक ये मैंने जिस तरह एक क्लॉक टिकिंग, यहाँ से एक लाइट पल्स जा रही है, इधर तक जा रही है, यहाँ से रिफ्लेक्ट होके वापस आएगी इस यहाँ तक। But if I have a frame, what I'm going to tell you now is that if एक frame है जो कि इस तरह move हो रही है, see the situation that the frame जिसमें ये happen हो रहा है, ठीक है? The frame is moving towards the right side at some velocity v, ठीक है? तो जो वो observer था जो कि rest पे था, that will not observe वो ऊपर नीचे जा रहा था ना, like this light was going up here and then it was going down here. In that frame जो कि right side पे भी move हो रहा है, yeah?
मैम आपकी वीडियो नजर नहीं आ रही।
मेरी वीडियो नहीं नजर आ रही, अब आ रही है?
नो मैम।
लाइबा आपका नेट स्लो है।
मैम आपकी स्क्रीन नजर नहीं आ रही।
स्क्रीन नजर नहीं आ रही मुझे।
You don't know. अब आ रही है स्क्रीन?
यस मैम आ
यस
रही
मैम।
थी।
वीडियो आ रही है?
यस मैम आ रही है।
अब
Okay,
आ रही है मैम।
Okay, so as I was saying that if I have a situation that there is one frame of reference, you could write, it's moving towards the right side. It's moving along the x direction with a velocity v, ठीक है? Which is relativistic velocity. It's moving close to this, the frame is moving close to the speed of light, like for example, 0.5 of times c, or say 0.8 times c. And then we have an observer that is at rest. So if we have an event such that there's a light pulse which is being sent out and then reflects from this mirror, it's in the y direction. In the y direction, there's a light pulse, it goes, reaches this mirror, then reflects and comes back. Because that frame is moving in this direction, don't you think that the light pulse will move in a triangular path for like this and then like this? Because वैसे तो this is the light pulse, it's going here, but because that frame is moving in this direction, so basically it's going to travel in a triangular path. Yes? पहले तो हम ऐसे ऊपर जा रहा था, फिर नीचे वापस रिफ्लेक्ट होकर नीचे आ रहा था. अगर वो स्टेशनरी फ्रेम होता, वो रेस्ट पे होता with respect to the other frame, फिर सीधा ऊपर और वापस नीचे आ जाता. And then there would be no time dilation because it's not, the frame is moving in this direction and the velocity of the light is in this direction. तो फिर उस केस में time dilation नहीं हो रहा. लेकिन in the situation where, these are difficult concepts and I hope that you can all try to understand this as much as we can. ठीक है? This is actually a special relativity is a course that you will be taught in the senior year. पूरा course होगा special relativity पे और पूरा course quantum mechanics पे भी होगा. ठीक है? So what I'm trying to say here is that यहाँ पे ऐसे situation है. This one is at rest. ठीक है? Observer here is at rest. But this यहाँ पे एक light pulse ऊपर जा रहा है फिर नीचे आ रहा है, लेकिन the frame is moving in this velocity, so the light will be observed to move in a triangular path. Yes?
Yes मैम, जिस हम किसी चीज का ग्राफ विद रिस्पेक्ट टू टाइम देख रहे होते हैं तो वो आगे आगे हो रहा होता है, इसी तरह ये लाइट भी आगे आगे हो रही है.
ठीक है? So now we want to analyze how we want to do some derivation of the quantity.
Excuse me ma'am.
Yes.
टाइम हो गया.
टाइम बस 5 मिनट और दे दे मुझे. ठीक है?
हम प्लीज डेरिवेशन
स्टार्ट कर लेंगे अभी. आज 5 क्लासेस थी तो
आज 5 लेकिन अब यहाँ तक में आए क्लास बन रही है.
मैम ये कल कर लेते हैं मैम.
ओके, लेकिन ये सिचुएशन समझ में आ गई है कि ये ट्रायंगुलर पाथ क्यों लेगा?
यस मैम समझ आ गई.
ट्रायंगुलर इसलिए है क्योंकि वो पहले like if I open the whiteboard again, ये बार इसको खोलना पड़ता है. Zoom was a lot easier I think to use, but जिस तरह हम पहले क्लास थे ये ज़्यादा इजी है.
यस मैम शायद मैम ये स्मूथ ज़्यादा चल रहा है, वो बहुत स्लो चल रहा है.
Yeah, okay. So if this observer is at rest and this frame is moving with velocity towards the x-axis, ठीक है? ये है x-axis, ये है z-axis, और ये है y-axis, ठीक है? So if there's a clock, we send out a light pulse here. This is called an event that's taking place in, this is S frame. This is S dash frame. So the clock is moving, the light pulse is going from here to here, then it will go here to here, but because this is moving in this direction as well, from this observer will appear to be going in a triangular path. And I guess if you want, we can continue the derivation in the next lecture, but I think we didn't do very much today.
मैम एक क्वेश्चन है थोड़ा सा.
Yes.
मैम अगर ये जो फ्रेम मूव कर रहा है इस नेगेटिव एक्स डायरेक्शन में, तो लाइट पल्स जो ऊपर जाएगी वो तो सीधी ही वापस आएगी, क्योंकि उसे बाउंड रखने के लिए तो कोई चीज़ है नहीं जो उसे बाउंड करके दोबारा उसी फ्रेम पे लाएगी.
यहाँ पे एक मिरर है, वो रिफ्लेक्ट होके यहाँ वापस आ रहा है. There's a whole like apparatus here, like we're talking about a situation जिसमें यहाँ पे एक मिरर है, उससे रिफ्लेक्ट होके वापस आ रहा है. तो अगर ये फ्रेम ऐसे मूव हो रहा है So apparently, according to this frame, वो triangular path move करेगा. Does that make sense? Like I will show you this PowerPoint. यहाँ से ऐसे नजर आ रहा है. So if this distance इसकी भी एक quantity है is equal to Pythagoras theorem हम apply करेंगे. This distance plus is equal to this distance squared plus this distance squared, and then we will get an equation for. We will manipulate the equation a little bit. And then we will see that we will get t is equals to t naught 1 over divided by 1 over b square minus c divided by c square. ये हम result derive करेंगे. ठीक है?
Okay, ma'am.
Any other questions? Any other questions?
No, no.
मैम अटेंडेंस लग रही है.
Yeah, attendance लग रही है. मैं download कर रही हूँ attendance list. ठीक है? Okay, so if there are no more questions, then our next class is on Thursday, I believe, right? Thursday.
हम अटेंडेंस अपलोड कहाँ करेंगे आप?
मैं वो AMS में करूँगी ना?
Okay.
Yeah. ठीक है? Let me check अगर attendance download हो गई है. I'll share options. Is this making sense so far? What we're studying?
मैम अभी तो स्टार्ट है तो थोड़ा थोड़ा तो समझ आ रहा है, लेकिन एक दफा आप लोग इसको रिवाइज कर लेंगे तो हो जाएगा. बाय नेक्स्ट क्लास इंशाल्लाह
करेंगे या उससे फिर समझ में आ जाएगा. ठीक है? अभी तो शुरू है तो इतना ज़्यादा आसानी से इतना नहीं समझ में आएगा, लेकिन gradually with time you will understand. ठीक है? So ये है आप सबका registration number 18 से शुरू होता है ना? नहीं,
18 से शुरू होता है.
18 से शुरू होता है. ओके, ठीक है. So आपकी attendance list भी डाउनलोड हो गई है. ठीक है? तो we can continue from on Thursday. ठीक है? And I hope that you're all not tired by the time we reach 3 o'clock, because you have classes during the whole of the rest of the day as well, right? Because in this course we need to use mathematical, काफी ज़्यादा mathematics है, तो we have to be able to think a lot in this course, like understand the situation और उसके हिसाब से calculations और ये सब करें. तो
मैम बहुत गलत टाइम पे ये क्लास रखी है मैम.
अच्छा. Because which other classes are you taking this semester?
मैम सोलर फिजिक्स है.
अच्छा.
डिजिटल इमेज प्रोसेसिंग है.
अच्छा.
स्पेशल डेटाबेस है.
अच्छा.
और स्पेशल वो है स्पेस फ्लाइट डायनामिक्स है.
अच्छा, okay. But I mean, what I'm trying to say is that in this course you need to use your brain a lot. ठीक है? Mind का use बहुत ज़्यादा है. इसमें mathematics है और you have to try to visualize and understand what's happening in the situation.
मैम अगर आप सुबह के टाइम फ्री होती हैं तो ये क्लास सुबह को शिफ्ट कर लें हम.
यस मैम, ऑनलाइन तो फिर भी हो जाता है, लेकिन ये है कि जब यूनिवर्सिटीज ओपन होगी फिर बहुत ये हेक्टिक हो जाएगा. 3 से 4
वो फिर आप कोऑर्डिनेटर से बात करें, क्योंकि मेरे मॉर्निंग पे दूसरी क्लासेस होती हैं ना. क्योंकि आई थिंक 3 o'clock is an okay time. I mean, मेरे लिए तो यही टाइम सूट करता है, क्योंकि मेरे मॉर्निंग में दूसरी क्लासेस होती हैं थोड़ी बहुत. क्वांटम एंड स्फेरिकल.
मैम इतनी कोई बड़ी बात नहीं है, कोई मसला नहीं.
हाँ.
यस.
Okay, ठीक है. So we will continue then on Thursday, and if you want, you can go through the PowerPoints I've uploaded on Special Relativity. You can go through the book as well. If you have, it will be easier to follow the lectures if you have a little bit of background information as well. Okay? I mean, you don't have to, but it's always good to. Okay?
Yes, ma'am.
Okay, any other questions for today? No questions? Okay, then I will close this meeting because ये room को lock करने के लिए कोई आया है. ठीक है? Okay, then see you on Thursday inshallah. ठीक है?
Okay.
Okay, Allah Hafiz. Hafiz.
Allah Hafiz मैम.
Hafiz.
the meeting.